Now we're going to look at systems of linear equations. So linear equations means equations like this one here. So that's a linear equation in x and y. It's x to the power of 1 and y to the power of 1. So there's no squares, x squared, y squared, or square roots or any higher powers. It's an equation that can be written in the form a times x plus b times y plus c is equal to 0, where a, b and c are just numbers. So you can also write that in this form, y equals mx plus c. So that's writing it like y as a function of x. And when it's written in that form, m tells you the slope of that line if you were to plot it as a line, and c would be the intercept on the y-axis. So if I plot this out, let's say that's x and that's y, and I plot y as a function of x, an equation of this type will give you a straight line. For example, like this. Now in that case, this point here will be c on the y-axis, because if you look at it, if you let x equal 0, you get y equal to c, and m there gives you the slope. So what that's telling you is, for every 1 you go over this way, how far this way do you go, or what's the rate of change of y with respect to x. So the first thing you're asked to do here is find the slopes of those lines. So I'll do one for you, and I'll leave the others up to you. So the first one is 2x minus 5y equals 20. So that implies that minus 5y is equal to 20 minus 2x, which implies that 5y is equal to minus 20 plus 2x, or y is equal to 2 over 5 times x minus 4. 2 over 5. So in that case, compare that to the formula above, mx plus c. That would mean that here m is equal to 2 over 5 and c is equal to minus 4. So the slope there is 2 over 5. So you can try the other ones down here. Next, they give you two equations. So if you've got two equations in x and y like that, these are simultaneous equations, and you should be able to solve them to get a value for x and a value for y. Well, one way of doing that would be to just plot the two of them and just see where they intersect, because the line that each one of those makes in the xy plane corresponds to the set of points that satisfy that equation, and the intersection will be the point that satisfies both equations, and that will give you the xy value, will be your solution for x and y for the two equations. So if I look at the first one, 2x plus y is equal to 5, that means that y is equal to 5 minus 2x, and on the other one gives us y is equal to x plus 2. So the slope of the first one has a y-intercept of 5. So when x is equal to 0, y is equal to 5. So let's say that was here. It has a slope of minus 2. So for every 1 we go over in the x, we go down 2 in the y. So let's say that looks like this. The other one has a y-intercept of 2 and a slope of 1. So if that was 5, 2 would be about here, and the slope here would be 1, so let's say it looks like this. And if we look here, this point here, whatever that is, we go down here to get the x value, we go over here to get the y value. That would be our solution for x and y. Now, that's only a rough graph, so that won't actually give us an accurate answer, but that's how you'd solve the equations, by plotting them out. You can imagine if you had 3 equations there, the third equation would give another line. Let's say that it looks like this. Chances are it won't intersect that point, so there won't actually be a point anywhere, a point xy, that satisfies all 3 equations. So in general, for equations in x and y, you could have two equations will have a unique solution, but three separate equations will have no solution. Two equations won't always give you a unique solution though. You could have the case where you have two parallel lines that never touch. So there you have two equations and no solution. Or it could be that you have two equations that give lines that just run right over each other. In that case, there's an infinite number of solutions. So most of the time, two equations will give one solution. But if they're parallel or directly on top of each other, you could have no solutions or an infinite number of solutions. And finally, if you were to try to do this with the elimination method, that just means going through the equations and solving them for x and y. So let's write them down again. 2x plus y is equal to 5. X minus y is equal to minus 2. So from that second equation, we can say that y is equal to x plus 2. So I can take this and I can substitute it back in here to get an equation with just x. So that's 2x plus x plus 2 is equal to 5. So that gives me 3x is equal to 3, implies that x is equal to 1. Now I can take that x equal to 1 and substitute that back in here to get a value for y. Y now is equal to 1 plus 2 is equal to 3. So on our graph above, x should have been equal to 1 and y should have been equal to 3. So that wasn't actually too bad, that graph. So that's how you solve it graphically, or solve it by just going through the equations, what they call the elimination method. So next we look at another method with matrices. Now, before we get stuck into the details, I'm going to show you another method, which is the inverse matrix method. Have a look at this matrix equation. If you multiply that out, you'll see that you get back those two equations here on the left. So if I multiply that top row there, I get 2 times x plus 1 times y, and that must be equal to 5. And the same for the bottom row. So that matrix equation is equivalent to that system of two linear equations there on the left. So if I give names to these things, let's say I call that A x equals b. So here, this matrix here is A, this is x, and this is b. Now, if I could find the inverse of A, I could multiply both sides of that equation by the inverse of A. Implies A inverse times A times x is equal to A inverse times b. That's if the inverse of A exists. So A inverse times A is just the identity matrix. So that's equal to this. The identity matrix times any matrix just gives you back that matrix. So Ix is just equal to x. And that's equal to A inverse times b. Now remember that x here, big X, is just this matrix that has x and y in it. So if I know the matrix X, I know the values of x and y. So solving this equation would be a matter of finding the inverse of A and then multiplying this thing on the right by the inverse of A. And that will give me my values for x and y. So let's just do that here and check. A inverse is equal to 1 over the determinant times, if we go back to our formula, you see that you swap the 2 on the diagonal and then minus the other 2. So that's going to be minus 1, 2, minus 1, minus 1. So go back to your notes on the inverse matrix. That formula is there to get this. So that determinant then, that is, if you go back to the matrix A, that's 2 times minus 1 times 1 is equal to minus 2 minus 1 is equal to minus 3. So the inverse of A is equal to minus 1/3 times this matrix so our solution should be x is equal to A inverse times B is equal to minus 1/3 times this matrix times B, which is that. So that's equal to minus 1/3 times minus 5 plus 2 and minus 5 minus 4 is equal to minus 1/3 times minus 3 and minus 9, which is equal to 1 and 3. So if xy is equal to 1, 3, that's the same answer we got before with the elimination method. So that's a quick example of the inverse matrix method for solving a system of linear equations. The nice thing about the inverse matrix method is that it works for a system of any size, as long as you can get the inverse matrix. So here on this page, instead of x and y, they say x1 and x2 and so on, like this. You know, an x1 and x2 here, and b is written as b1 and b2 and so on. But if you have a read through this, that's the same thing. This is a 2 by 2 case. It's here as a general case for a matrix of any size. Let's look at some cases now for when you can and can't use the inverse matrix solution. So the first case here is when your vector b, or the matrix B on the right side of the equation, is not equal to 0, or not equal to the null vector, that is, or null matrix, that is a matrix full of zeros. B not equal to 0, and also determinant of A not equal to 0. So this is the nice case. That's like the case we just looked at. In that case, since the determinant is not 0, we know that the inverse exists. And since the inverse exists, we can just find it, multiply both equations by the inverse, and we get this solution for x. But this is for the matrix x. That's what that little bar means above it. So that's that x bar is the column vector that contains all of the variables we're trying to solve for. So in this case, case 1, we have a unique solution. So we get one set of values, one value for each variable that solves the system. Case 2 is, again, we have an invertible matrix, but this time b is equal to 0. So if you think about this case, A times x equals 0, let's try and do our inverse matrix method. But when we do that, on the right side we end up with A inverse times 0, which is going to be 0. 0 here not being the number 0, but a null vector, a vector or a matrix of whatever size you want, a column vector that just contains all zeros in it. So that means that x is equal to 0. So if you have a system where there is an inverse, where the determinant is not 0, but that vector, that column vector on the right, is 0, then the only solution to that system is going to be that the vector x is also equal to 0. So all the variables that you're trying to solve for are equal to 0. You call that a trivial solution. Case 3. What if b is not equal to 0, but the determinant is? In that case, the inverse does not exist. So in that case you either have no solution or infinitely many solutions. That's like the cases I talked about on the graph, where the lines were parallel and never intersected, or where they were directly on top of each other, where you had either no solution or infinitely many solutions. So the case where b is not 0 but the determinant is like that. In case 4, where b is equal to 0 and the determinant is equal to 0. In that case, the inverse does not exist and the system has infinitely many solutions. So in the case where b and a are both 0, or b and the determinant of a are both 0, the system will have infinitely many solutions. There will be solutions, but there will be infinitely many. So those are the 4 cases. So here you're given a system and you're asked, when does it have a non-zero solution? So if you go back to the cases before, b here is equal to 0. These are all zeros. So for that to have a non-zero solution, the determinant must be equal to 0. Because if the determinant is not 0, but that vector on the right, b, is all zeros, which it is, then the only solution would be the trivial 0 solution. So the question here is to find the value of k for which the determinant of the matrix that you get when you put this equation into matrix form is 0. So I'll give you a quick hint for how to put that into matrix form. It's going to look like some 3 by 3 matrix times x, y, z is equal to 0, 0, 0. So the first row here would be 1, 5, 3. I'll leave you fill out that matrix yourself and have a go at that question yourself. And the same with the other two. So just remember, you need to write your matrix, find the inverse if it exists, and then A inverse times B is equal to X. So have a go at those examples.